This is a video going through how to do coordinate geometry proofs with variables as the coordinates instead of integers like we're used to. So for the first one, given vertices of quadrilateral math are 0, 0, b, c, a plus b, c, and a, 0, prove that the diagonals bisect each other. So you might be thinking to yourself, how do I even draw this picture? Well, it's a quadrilateral, so I know that means it has 4 sides, and the only rule for when you're drawing these sides is that the order of the letters they give you, so they see M, A, T, H, those letters either have to go in clockwise or counterclockwise order as you're ordering them. So I'm going to do counterclockwise. So M, maybe A's over there, maybe T's over there, and maybe H is over here. Your picture doesn't have to look like this. It just needs to be some shape with 4 sides. That's it. And it wants us to prove that MT and AH bisect each other. Now, if these coordinates were just numbers like we're used to, we would do the same thing we always do, where we just find the midpoint of AH and find the midpoint of MT, and that would be enough to prove that they bisect each other or cut each other in half. But when we have coordinates that are variable expressions instead, the process is exactly the same. As long as you know that midpoint formula, the average of the x's, the average of the y's, you can just plug in and show that you get the same expression for both midpoints. So for MT, what that's going to look like is my first x-coordinate 0 plus my second x-coordinate for t, that's just a plus b. That's that whole x-coordinate there, divided by 2. And my y-coordinate for m is 0, plus my y-coordinate for t is c, divided by 2. If I want to clean this up a little bit, I don't really have to have that plus 0 there. So I could write this a little bit cleaner as a plus b over 2 as my x-coordinate for that midpoint, and c over 2 is the y-coordinate. So if these segments do bisect each other, which they're telling me to prove so, it has to be true. I want to end up getting this same expression right here when I plug into the midpoint formula for AH. So keep that in mind as you're going through this. So I do the same thing. My x-coordinate for A is B, plus my x-coordinate for H, which is A, divided by 2, and C, the y-coordinate for A, plus 0, the y-coordinate for H, over 2. Again, if I rewrite that, I'm trying to get it to look like MT's midpoint. B plus A is the same as A plus B. Remember, addition is commutative. And C plus 0 is the same as C. So I could just have C as the numerator there. So if I'm looking at these two midpoints, the x-coordinate is A plus B over 2 for both of them, and the y-coordinate is C over 2 for both of them. So if I want to prove that these diagonals do bisect each other, this is enough work to justify that. We would just need to say that since the midpoints for both these segments are the same, these segments must bisect each other. So even though we don't end up with numbers as the coordinates, these are still the exact same expressions. So regardless of what A, B, and C is, these are going to work out to be the same midpoint. Number 2. Given the vertices of quadrilateral OPQR are 0, 0, 0, n, h, n plus k, and hk, prove the triangle OPQ and triangle QRO have congruent side lengths. So before we start any of these proof problems, we need to have a game plan going into it. So if they want me to prove that triangles have congruent side lengths, I'm probably going to need to use that distance formula, d equals the square root of x2 minus x1 squared plus y2 minus y1 squared, in order to find the lengths of the sides of these triangles. But just to get an idea of what these look like, I'm going to draw out that quadrilateral OPQR. So again, I'm going to label them in counterclockwise order, and it doesn't matter what your picture looks like as long as it's a quadrilateral, because I'm not putting this on a coordinate plane, because we don't know what n is, we don't know what h is, and we don't know what k is. So triangle OPQ, OPQ, so I would need to connect these so we have that third side of the triangle, and then triangle QRO. So it looks like they're talking about this triangle right here and this triangle right here. So if I want to prove that they have congruent side lengths, we could just plug into the distance formula a bunch of times to show that they all have the same expression when you plug into that formula. But the question is, how many times are we going to need to plug into that distance formula? I know we're going to have to find the distance of OR, plug in the coordinates for O and for R, and then hope that it's the same as one of them for the other triangle over here. But if you're a little clever, you won't have to do that 6 times for each side of the triangle. You only have to use the distance formula, in this case, 4 times. The reason being is because if you look at side OQ right there, side OQ is a side of triangle OPQ, and it's a side of triangle QRO. So we could say right off the bat that OQ is going to have a congruent side length to OQ, because it's the same length for both those triangles. Since they share that side, this is a statement we could take for granted. That's just called the reflexive property. And we'll use that a little bit more when we're doing formal proofs later on. So what this looks like when we start plugging in, for the distance between O and R, so the length of that side OR right there, that's just going to be h minus 0 squared plus, give myself a little more room here, k minus 0 squared. And I'm just taking the x coordinates and subtracting them, and taking the y coordinates and subtracting them for O and R. So I'm just left with h squared plus k squared as my distance between O and R. And there's nothing more I could do to simplify there, so I'm going to leave it just like this for now. And I'm hoping that one of the other sides of that OPQ triangle also have that expression as one of the side lengths. So I'll find the distance between R and Q now. So my x coordinate for Q is h minus my x coordinate for R, which is also h squared, plus, now be careful here, n plus k minus k quantity squared. A lot of good things happen here. H minus h is just 0 squared, so that's just going to be 0. And n plus k minus k is just n squared. So what this ends up turning into is just radical n squared, or just n. So the distance between R and Q is just n. So hopefully when we plug in for the other two sides, OP and PQ, we get these same expressions. So I'm going to zoom out a little bit. The distance between O and P is the square root of, and we do the same process where we just plug in the x coordinate of P, which is n, and we subtract the x coordinate of O, which is 0, plus the y coordinate minus the other y coordinate. And it's looking like this is starting to look like the distance RQ, right? Because that just becomes radical n squared. 0 squared is just 0, and n minus 0 is just n, which just becomes n. So we already have that OP is going to be the same length as RQ. So I'm going to mark that in my picture. OP is the same as RQ. So that's one pair of sides that we have. And we also have OQ is congruent to OQ over here. And the way we mark that usually is just with an X on those sides. So we want to get some math here to prove that PQ is now congruent to OR. And we could do that same trick where we just plug into the distance formula. So our coordinates for, which side are we missing? OP, we need PQ. And we do the same thing. The X coordinate for Q is H, minus the X coordinate for P, which is 0. And be careful with this next one. The X coordinate for Q is the Y coordinate for Q is N plus K, minus the Y coordinate for P, which is just N. And again, we have this N minus N thing happening here where we have that 0 pair, so those sum to 0. And we're just left with radical H squared plus K squared. Is exactly what we had for side OR. So in this case, we do have it that triangle OPQ and triangle QRO have congruent side lengths. The reason being is that when we plugged into the distance formula, we showed that PQ was congruent to OR, we showed that OP is congruent to RQ, and OQ is congruent to OQ by the reflexive property. So you don't need to write a full statement reason proof for this, but you would need to be able to explain yourself in a couple sentences of why this work, even though there are no numbers for some of these expressions, still justifies why these two triangles have congruent side lengths. So regardless of what H, K, or N is, these side lengths have to be congruent.